Olá, espaçonauta! Pessoal, prometi para vocês esse vídeo aqui, né, que é exatamente a live que o pessoal lá do Gemini South fez, né, onde capturaram a melhor imagem do 3 Atlas até agora. Né, aquela imagem que eu divulguei várias vezes, em vários vídeos para vocês aí. Né, essa live é muito legal. Ela foi traduzida para a gente pelo Alfredo Lopes Moraes, de Portugal, né? E ele debruçou lá, fez ela durante vários dias. Eu tive que pegar e dar uma enxugada, porque ela estava grande demais, ainda ficou um pouco grande. Só que eu acho muito legal para vocês assistirem, porque, primeiro que isso aí é uma iniciativa ímpar de um observatório renomado com um telescópio de porte gigante, transmitindo ao vivo um trabalho de captura de imagem e espectrometria. Então é muito legal isso. E aí é muito legal também, porque os astrônomos responsáveis ali por essa captura, por essa live lá, eles explicam várias coisas e dão, falam muito do que a comunidade científica de verdade está achando do 3 Atlas, como é que funciona, né? E vocês vão ter a oportunidade de ver, na verdade, a captura e, na verdade, um trabalho científico sendo realizado ao vivo, né? Ele não está ao vivo aqui mais, mas ele foi transmitido ao vivo para quem assistiu na época, né? Esse programa aí é uma iniciativa da Norlab, que é uma das que gere aí o Observatório Gemini, né? E ele foi liderado pela Karen Mitch, que é astrônoma do Instituto de Astronomia da Universidade do Havaí. E ela é justamente especialista em cometas e planetas. Então ela dá explicações fantásticas aqui, tá? Esse programa, ele faz isso há algum tempo com vários objetos celestes. Ele se chama Shadow the Science, né? É na sombra do cientista, que é justamente acompanhando os cientistas, tá? Vale a pena, gente, vale a pena. Assiste com calma, assiste o conteúdo, olha com calma. Vocês vão ter a oportunidade de ver o telescópio sendo calibrado, né? São várias coisas feitas. O processo de calibração, gente, demora mais do que a captura da imagem. É incrível, o trabalho é muito bacana. É como se vocês estivessem dentro lá do observatório fazendo a observação com os astrônomos. Muito bacana. E observem as explicações, né? Inclusive, a Karen, ela coloca assim, ela coloca o Eiffel Web em xeque, fala que é um absurdo ele tá fazendo isso aí que ele tá fazendo aí, esse auê todo que ele tá fazendo aí. Bom, mas não vou dar spoiler mais não, né? Já deixa aqui nos comentários o seu abraço e agradecimento pro nosso amigo e colaborador Alfredo Lopes Moraes, de Portugal, porque graças a ele a gente tem acesso a conteúdos incríveis como esse. Né? Então aqui é o único canal onde você vai ter acesso a isso em português, graças a esse trabalho voluntário e abnegado do Alfredo aí, em prol da ciência e nos ajudando aqui. Né? Então vamos lá para o vídeo que está imperdível.
Welcome to this special session, a close encounter with an interstellar visitor from the Gemini South telescope. My name is Jamika Marshall, and I am the Shadow the Scientist Programs Manager. Now, for those of you joining me virtually, I'm looking kind of away from the camera a little bit because I do have a live audience here. I'm hosting from the Mauna Kea Visitor Information Station, so I'm trying to look at them and you as well. Now, we have multiple science hosts today, many special guests, but our main science hosts will be Brian Lameau and Karen Meat. Now, our observing staff there in Gemini South is Pierre King in the operator's chair and Carlina Silva as the observer. And we'll find out a little bit more about those different roles as we move on. Now, Shadow the Scientist is an initiative that's brought to you by a fabulous team at the University of California, Santa Cruz. Now, the International Gemini Observatory consists of two 8.1 meter optical infrared telescopes, and these are twin telescopes located on two of the best observing sites on the planet. So those of you here with me, you know, we have Gemini North just up the road here at the summit, in the summit region of Mauna Kea. And of course, those of you joining virtually, of course, you know, we are going to be looking, observing with Gemini South. Now, the Gemini South telescope is located on a mountain in the Chilean Andes, as you can see here, called Cerro Pachon, where the air is very dry. Let me restart this. The air is very dry, and there's negligible cloud cover that makes this a prime telescope location. Now, both of the Gemini telescopes have been designed to excel in a wide variety of optical and infrared capabilities. Now, by incorporating technologies such as the laser, guide star adaptive optics, and multi-object spectroscopy, astronomers in the Gemini partnership are able to explore the universe in unprecedented depth and detail.
Hi, Jamaica. This is super exciting to be joining you today from all over the world, really.
Yes.
And having participants from all over the world. So super excited to see the Akula School here, and super excited to see school students from Hilo and La Serena and everywhere in between. So I'm Brian Lameau. I'm a staff scientist here at Gemini North. As Jamaica mentioned, Gemini has two sites, one located on Mauna Kea. That's the one I primarily work with, and I'm based in Hilo, Hawaii. And then I work on not things in the solar system, so I usually look way past the solar system.
Hi, everyone. This is really exciting. I've never done something like this, so I'm really excited to hear all your questions and to see the observations come in live. I'm an astronomer at the University of Hawaii's Institute for Astronomy. I've observed both in Chile and, of course, on the summit of Mauna Kea and remotely. My title is equivalent to professor. It's called astronomer. So astronomers tend to do scientific research, but we also teach classes. We do outreach and have a lot of other obligations with our job committees, but I'm also involved in space missions. So it's a whole breadth of exciting activities, of which I'm really excited for today.
Hello, everyone. My name is Su. I'm an astronomer at Gemini Observatory. I used to be in Hawaii, lived there for 7 years, but recently moved to Tucson. I have maybe somewhat similar to Karen. I have split my time between doing research and actually observatory support work. My research mostly on stars and the planets and debris disks, so a little bit related to today's topic. And my service work, I used to do a lot more instrumentation, but now I'm doing more user support and user engagement and work very closely with our chief scientist, Elena. So I'll pass on to her.
Thank you, Suhi. Hello, my name is Elena Sabi. I am the chief scientist of Gemini. And prior to that, I was working at Space Telescope on the Webb mission. I studied star formation and stellar evolution in the Milky Way and nearby galaxies.
Aloha, everybody. My name is Emily Peavy. I am the Senior Education and Engagement Assistant here at the Gemini North Telescope based in Hilo. My background is in astronomy. However, I discovered that I like talking with people, and a lot of astronomers don't like talking with people as much as I do. So a lot of my focus ends up being more on the education engagement side and thinking about how we can make all these really complex ideas and discoveries and things that are happening in astronomy more communicable and to be able to share it with all of you. So we're so happy to see all of you today. This is such an exciting event of us being able to observe this comet, and we are all really, really looking forward to being able to see some of the data for this interstellar comet be captured in real time.
Hey, sure. Thank you. This is fantastic to be here with all of you. My name is Bryce Bolin. I am a research scientist at Eureka Scientific. Most of my time is spent on doing observations, but I also do quite a lot of service work for the community. My main focus is in asteroids and comets of the solar system. You can see there's a comet behind me here. This is one that I discovered called C2022 V2 ZTF. And among other things, I really like these interstellar objects. I've been lucky to observe and study all three interstellar objects known so far: One-Eye Oumuamua, Two-Eye Borisov, and now Three-Eye Atlas. So this is just a prime time excitement for me.
Yes, we're here in the lecture hall. Well, my name is Manuel Paredes. I'm the outreach manager in Chile, and I'm happy to be here with a group of students from the Astronomy Academy of the Colegios Sagrados Corazones in La Serena. Can you hear me?
Yes.
Yes, we can.
Yes.
So say hello. Digan hola.
Hola. Hola.
Hola.
So very exciting to be here. I'm translating what you are, all of you are saying. We are very, very, very happy to be here and to have this chance, this opportunity to know more about Cometa and the work that we do in Gemini South and Gemini North. Thanks, Brian.
Okay, so we are here at the control room at Gemini South. We are taking calibrations, the final calibrations, and then after that we are going to do some of the tuning of the telescope. My name is Carlene Silva. I am a science operations specialist, also known as SOS. And my colleague here.
I am Piera Aki. Also, I am SOS. And in this night, will be the operator of the telescope.
Yeah, and I will be running the instruments. And conditions are good. The sky is mostly clear. We have some thin clouds passing by, although they are not over the summit. So we are taking the twilights, and yeah, we have a short observation before going to the target of tonight, and yeah, we are running around here to do that. And if you have any other questions, we can answer along.
So Carlene, like right now it's what, about 20 minutes after sunset there? And you guys are taking twilight flats, imaging flats, is that right?
Yes, we are taking imaging twilight flats to use for your observations, actually. So we just got the U-band. We had to do that before the sunset. And now we finished taking the G-band, and I have some pending G-band, but with 4x4 beaming. And then after that, we are going to tune the telescope, do a short observation, and then the idea is to view to the comet.
Great. And Carlene, might you tell the participants where you are relative to where the telescope is? Are you on the summit right now?
No, we operate the telescope from the base. So we are in La Serena, and we are connected to Cerro Pachón. Yeah, and we control everything from here. We have cameras to see the sky condition. We have cameras inside the telescope. We have sensors, temperature, all the environment monitoring. So we have a good idea how conditions are there, if it is safe to operate, because
this is a public page here. Anybody in the world can go to it. This is the Gemini South status page. We also have an equivalent one for the North. And there's a ton of information. So as Carlene mentioned, all of these observations are done remotely, in the sense that both here in the North and in the South, we're not physically at the telescope. And that it's very hard to take observations when you're not physically at the site that you're observing from. And so you need a ton of information to be able to assess, first of all, is it safe to operate? So this was the most important question. And this is the question that Carlene brought up first. And in fact, Piera's job, one of her many jobs tonight, is to make sure that everything is safe for the instruments and for the telescope. So if there's any impending danger from the weather, here in Hawaii, the Kilauea can go off, and that's not a threat to the telescope in the sense that lava is going to envelop the telescope, but it does off gas, and with humidity, that can be a problem for our optics and for our instruments. We also have thresholds for wind speeds, as Carlene mentioned, there's a lot of cloud cameras. So any sense that there's impending precipitation, we will certainly close down. So we have a bunch of instruments that are available this evening. You can see this instrument availability. GMOS South is the instrument that we're going to be using this evening for these observations. Actually, Carlene mentioned that there's another observation that's coming. This is from the GHOST instrument, and we might talk about that a little bit later. And then there's one other instrument called Flamingos 2, which is a near-infrared spectrograph and imager, and we can talk about what those mean a little bit later. But since we're we're about 15 minutes away, 20 minutes away from what we call 12-degree astronomical evening twilight. So that means when the sun is 12 degrees below the horizon after setting. This is when we're going to start taking the observations of the interstellar visitor, or that's the plan anyways. And so I wanted to pass to maybe Elena and CE to explain how these observations came together, and then we could talk to Karen about what these observations are of and what they might mean.
Just a little bit, my specialty, for my whole of my career has been comets. And, there's a nice picture of one behind me. The reason that scientists get so excited about comets is they're the leftover building blocks from the process of forming a solar system. It's like an archaeologist able to go back in time and look at the details of the process that build planets. And many think that comets could have brought some of the essential ingredients for life to the inner planets, water and organic materials. So that's why comets in general are very exciting. Now, during the process of forming a young solar system, all these building blocks are coming together and forming bigger and bigger pieces, some of which eventually become planets, but some of the leftovers get tossed out into the outer part of our solar system, where later on, billions of years later, they can get perturbed inwards and pass through the inner solar system. When sunlight heats up the surface of these, they're made of ices and dust. You develop the beautiful tails that you can see behind me. Interstellar objects are building blocks of other solar systems that got kicked completely out of their home star and just by chance are passing through our solar system. And so this is really exciting because we have something close that we can look at with our telescopes and study in detail. And one of the ideas is, are the processes of building planets exactly the same everywhere? Do they start with the same chemistry? Is it the same process to combine the materials? Are the building blocks the same size? So whenever you get one of these, we've only had 3, everybody wants to use as much telescope time as possible to get details, to see if they're similar or different to the bodies in our solar system. So the first one was discovered in 2017 by the Pan-STARRS telescope in Hawaii. And it was really unusual in the sense that it did not look like a comet. It looked like an asteroid. It didn't have a big tail. It was very small, roughly a couple hundred meters across. And as it passed close to Earth, passed around the sun, it was found to be accelerating, which suggested it did have gas coming off its surface, but we had such a short window of time that we couldn't observe it. Now, the second one that was discovered, Borisov, in 2019, it was discovered by an amateur observer doing something that the big telescopes usually don't do, and that is looking close, very close to the horizon in twilight. And this one looked like a regular comet. It had a nice tail, and we had a long period of time to observe it, a couple of years, unlike for the first one, Oumuamua, where we had a week where you could get a lot of data and then a little bit of data for a couple more months. So it turned out that Borisov looked more like a regular comet. It was a little bit different in its chemistry from the comets we see in our solar system. In other words, it had a lot of carbon monoxide, which we often see in our comets in the solar system, but this one had a lot more. And then finally, this third one was discovered this summer, July 1st, by the ATLAS telescope, which has been developed by astronomers in Hawaii. And it was a lucky find because it was discovered projected against near the center of the galaxy, meaning there's a huge bunch of background stars, making it very hard to see. But this one too looks like a typical comet in the sense that it's getting the development of the tail. It's still approaching the sun. What we're hoping to do tonight is to look at get some pictures of the comet to see what color it is, because that gives you a hint of the chemical makeup. We want to see how much of a tail there is. And then we're going to take a spectrum, which is a way of splitting up the light into many, many different wavelengths to give us a chemical fingerprint of what's in the gas. And so we're hoping to start to see the typical chemicals that we see in normal comets. Now, most comets in our solar system are made mostly of water, ice, and dust. They have some carbon dioxide and carbon monoxide, but mostly water. And as they start to get warm enough that the water leaves the surface and pushes the dust off, the very first molecule we see is typically cyanide. This is not a very abundant molecule, but it interacts with sunlight really strongly, and it's easy to see. And in fact, that's why in 1910, when people were thinking about Halley's Comet, we were going to pass through its tail, and they were very worried because cyanide's poisonous. So we're hoping to see that tonight. We're hoping to see cyanide. It's been seen on some other telescopes, but we want to watch how it gets stronger as we get closer to the sun. So I hope that gives you a very quick overview of comets, interstellar objects, and it's looking like this one is very different from the others we've seen before, and that's what's exciting. We just don't know what we're going to see tonight. We often see in our solar system comets that are rich in CO2, but the ratio of how much carbon dioxide to water is unusual in this one. But we're still fairly far from the sun, and normally, ices like carbon monoxide or carbon dioxide, they start to turn into a gas at very, very low temperatures. And so we're not as close to the sun as you would like to be for water to be really active. It's sort of the slowpoke in the race. You have to be pretty close to the sun before water is very active. But even so, this comet looks really rich in carbon dioxide, or for those of you that may have played with it in school, dry ice. The cyanide is dragged out when the water comes off the surface of the comet, or potentially when carbon dioxide is coming out. It's either in the form of hydrogen cyanide, and this organic molecule, when it reacts with sunlight, the sunlight is intense enough that it can break apart that molecule, giving us just the cyanide, which is a carbon and a nitrogen. So typically we see it anywhere from 2.5 to 3 astronomical units from the sun, which is about the distance where we are at now with 3i. It's either coming from these organic compounds or sometimes off of even more massive molecules on the dust grains. So that's what we're hoping to see. And it's been seen at other telescopes now, but we would like to see how it's increasing as we get closer to the sun. And interestingly, one of the telescopes in Chile at the European Southern Observatory has now seen nickel lines, emission from nickel in the cometary gas, and that's been seen on other comets also. So it's starting to come to life in terms of showing us the chemical fingerprints, which is exciting.
I'm sharing right now I'm actually sharing Carlene's screen. So these are the actual control screens that are being used at the Cerro Patron base facility, and these are instrumentation screens that are being used to set up the instrument that's receiving the light from the telescope.
Yeah, sure. So GHOST is actually our newest instrument at Gemini South, and it does high resolution spectroscopy. So maybe Elena will first tell us what is spectroscopy.
Okay, can I actually share my screen for a moment?
Yeah, absolutely. Yeah.
When we look at a star, we only see a small fraction of the light, but actually every astronomical object, including the comets that we are looking today, spread the amount of shows light in a very broader range of wavelengths that goes from the gamma rays to the radio. And astronomers want to study astronomical objects in all these wavelengths because they carry different amount of information, including the energy of the object that we are looking, the temperature, the mass. All this information can be extracted by simply looking at the light of an astronomical object at the various wavelengths. And the highest is the resolution that you can get, the more information you can have. So when we look at an image, it is very complex and it is very difficult to appreciate all the characteristics, what is emitting what. So what we do usually is to slice the light in small portion by using what are called filters. And these allow us to reduce what we see in a much smaller detail and appreciate what is contributing to the various images. So here you can see one element that is helium. It's very faint and it's just a little bit of nebulosity in the center. But then if we look at the oxygen or at hydrogen, we can see that they come from different parts of this region. This is a very effective way to isolate where some elements are coming, but is not giving us all the information that is included in a spectrum. To get all the information, what we do is to take as much light as possible and stretch it, as Karen said before, over what is called an electromagnetic spectrum. And this allows us to see all the components that are, for example, in this range, and also to see if there is something that is coming between us and the source per se. So we take a source, we look at the spectrum, and what we see usually is that there are thin lines or broad lines that are on top of the spectrum. These are elements that are absorbed by the atmosphere of the star. The light is coming from the center of the star, and then the elements are absorbed by the stars. When we look at the comet is not emitting light, it's reflecting light, so it almost works as a mirror. But what we can do is to look at where these lines are found, and this is very specific of every different chemical element. Every single line that we see in a spectrum comes from a very specific element, and they are always found in the same order. So they are really the fingerprint of the chemical composition of an astronomical object. And usually, well, we have different types of spectra. I didn't know that I was saying so many things at that time that I prepared this presentation. But you can see that this is what comes from the source before it's intercepted, and then you can have lines that are in emission if a gas is excited, as it happens, for example, in some neon line, or in absorption if the gas is stealing energy from the star. So when we look at this type of spectra, we look at where these lines are, how broad they are, their shape, their characteristic, and this tells us all the physical characteristic of an object. And so this is a typical spectrum of, I think, an AGN. But we can use this type of information to analyze what we are going to see in our comets today. And the spectra that we will see will be very different from this object. And this is another, so by looking at the characteristic of the spectra, we can understand what object are we looking at, what is the chemical composition, that it is the goal of today, and the temperature of the object that we are looking, the gravity, all this information. So GHOST is a particularly interesting instrument because it is a very high resolution spectrograph, and so it can give us an incredible amount of information about the chemical composition and the characteristic of the object that we look.
We're throwing a lot of technical terms around, so but a breakdown of a few things. Everything that you guys have seen so far has just been us calibrating instruments as we get ready to shift over to this observation. So that's calibrating images based off of what's going on in that specific section of the sky, what's going on with the telescope. Real quick, since you referenced the diagram of the telescope, but I'm not sure if we had a chance to walk people through exactly what's going on in that diagram.
This one here?
Yeah.
Yeah.
So that's the light path of the telescope.
Right. Yeah. So this is the light path of the telescope. This is a side view of the light path of the telescope. And yeah, as I mentioned earlier, so the light comes in from the object that's being targeted, as well as the background, the sky. And then it hits the primary mirror, goes to the secondary mirror. There's actually a hole in the primary mirror. It's a little tube, and then it goes down into our instrumentation cage. And this is where we have a variety of different instruments. And so some telescopes, like on Mauna Kea, for example, Keck or Subaru, they will usually use one instrument per night, maybe two, most three. And those are usually done in blocks. So you do like the first half of the night, this observation with this instrument, and then the second half of the night with a different instrument. We switch between instruments all the time. In fact, the movement between instruments is like faster than the slew speed, and the slew speed is pretty quick. And so we were just taking an observation with Ghost, which is at the bottom port here, and that actually, in those cases, our tertiary mirror moves out of the way and just lets the light through to the bottom. And then we switched over to this GMOS observation.
Yeah, I remember observing a long time ago with someone who'd not been to the telescope before, and they were getting impatient. They said, "Are we ever going to get onto your object?" And of course, all of this other stuff is or once you get onto the object, the science won't mean anything.
Exactly, yeah.
That's a great perspective, Karen.
Yeah, so we have all this build up. Yeah, so actually we had previewed that we were going to be on the target maybe a half an hour ago, but we had software issues, which happen all the time. We have an extremely complex environment, software environment, and hardware environment. But also calibrations take a long time, and they are very important, as Karen said. If you don't take them right and in the right order and in the right setup, and analyze them well, you can see things that are intrinsic not to the source itself, but to and that's not what you want. So I think we're slewing there, or we've slewed to 3i now.
Yeah, okay.
And so
we are in position.
So since this is what's called a non-sidereal.
Yeah, right now I'm waiting. So we are guiding and waiting the telescope to optics to converge. So I need the telescope astigmatism to converge, and then we can start taking the images. I have everything set up here.
So Carlene, I have your strip tools up. Do you mind explaining to people, if you don't mind, what you're looking at and what you're hoping to see?
Okay, so when we say we are guiding, the telescope is calculating the focus. So we select one star that we are going to take images of that constantly over the observation. And we are going to keep it on focus and also do corrections to the mirror, to the M1 based on that. One of them is the astigmatism. I guess several of us have astigmatism in our eyes, and the telescope also has a little bit of astigmatism because it's very big and deformable, so we need to correct that on real time. For corrections, we use a tip tilt, so there is something vibrating a frequency that is the same. Is the same as the system needs to correct the imperfections. And also we have, here you can see the guide counts of that star. So we have 20,000, and you need to keep an eye on that, because if they are stable, then conditions are good. But if they change, it could be clouds, could be the scene variations. So we keep an eye on that. Here you can see there is no winds. When I say it converges, that means the blue line and the red lines are together. So they see they converged. So I can start taking the first image. It's a 30-second image.
And there's one value on there that I want to point out, which is this is the center panel on the left side. This is what you were referring to for checking the astigmatism. And the M2 focus. And then there's a seeing estimate from the peripheral wavefront sensor. And this, so before, if people remember, it was reading 1.26 when it was pointing at the horizon at 23 degrees. It's now reading 0.38. That is a considerable improvement. So we are pointing now at what, 60 degrees elevation or so? Yeah, 60 degrees elevation. So looking through a lot less atmosphere. But this is seeing that is extremely good. So this is 0.4 2/5 of an arc second. So however many fractions of a fingernail that is. I'll let Emily do the math.
I will say that's so the term seeing is referring to our atmospheric conditions and how atmospheric conditions are going to be affecting our observations. So we want the seeing number to be as low as possible. So that's why, like, oh, we're getting super happy that it's dropping really, really small.
Brian, we have the first image. It's very nice.
Oh.
Okay, everybody.
Oh, nice.
Yes, look at that bad boy.
Nice tail.
You can figure out who's all the nerds on the call because we're all like getting in down here.
Very cool. This is even in the I band, I think, right? So, yeah, okay. Wow, it didn't look like that last time I saw it. And this, keep in mind for everybody, this is a raw image. So this is not even like, I mean, this is just directly from the telescope right now. It still has all the defects. You can see all the various like vertical stripes and the gaps and everything. That orange thing isn't real. That's not on the detector. That's just the software that we're using. But you can see the background stars, and then you can see the comet right in the middle there. So yep, we're there. And
so Karen, one thing go on, Karen.
You're looking at a piece of what would have become a planet in another star system, and we will never know where it came from because it came from a long time ago and there's so many stars out there, but this is a building block from somebody else's home.
I like that phrasing.
Yeah. I heard actually, Karen, that there's some supposition that it came from the thick disk of the Milky Way, so that it may even predate our solar system.
Yeah, that's possible. The problem with tracing it backwards in time, no matter how accurate you measure the path, is that everything is moving. And so it's not just about measuring the path of this object accurately, but it's knowing the paths of all stars accurately. And everything has errors in measurement. And so the farther away it gets, the errors build up, and eventually there's too many errors. You can never figure out exactly where it came from.
So Karen, I'm wondering how this initial data of just being a raw image, how this compares to like Oumuamua observations, with Oumuamua being so much smaller. And
well, Oumuamua was maybe so much smaller. This one, we have an upper limit to the size. And of course, Oumuamua did not have a tail. It would have, on an image like this, just looked like another one of the stars. So this one's really exciting. This is a much bigger tail than when the last time I saw it. And by looking at how the tail spreads out and what the different filters, what the different wavelengths tell us, we can get some estimate about how big the tiny little dust grains are. They're typically very small, micron size, so about the size of particles in cigarette smoke, so very tiny. But once they leave the comet, they no longer know that the comet is there. Instead, they're moving around along the orbit of the comet, but sunlight actually gives them a little push. And so that's why typically the tail spread out. Like behind me, you see the sort of whitish yellow tail. That's the dust. That's the reflected sunlight. And then the blue tail is the gas. And that's this one is probably, I'm thinking carbon monoxide. This is gas that got ionized, and now it's got all this beautiful structure because the sun's magnetic field gets tangled up in it. So I will be really interested to see what this looks like once we've calibrated it. I bet you the tail's a lot longer than what we can see in the image.
Yeah, and I'll just mention as part of this sequence, so this is just one band, meaning one color, and we're going to be taking 4 different bands in this sequence. So this is the reddest of the 4, and we're going to get progressively bluer. And so the different constituent components of 3i will shine differently in those different colors. And so hopefully in the end, we will have an expert at image processing put together a very beautiful picture of this. Maybe an expert that we have in the room right now.
Now, typically all these comets, they reflect more red sunlight than they reflect the blue light. And that's because typically they have a surface that's rich in organic compounds. Red alone doesn't mean it's made of organics, but it does mean that it could be organics, or it could be that it has something with iron oxides in it. You know, Mars doesn't have organics on its surface, but it does look red, and that's because of all the iron. Now, if you had a lot of ice mixed in with the dust, if it was dominating things, the ice reflects more blue light than red. So you may get something that looks more gray or even reflects the blue better. So we'll see once we get all of the data.
So while the images roll in, so I think we have another probably maybe 5 to 8 minutes of imaging. I was wondering, Emily, if you wanted to talk a little bit about Oumuamua.
Yeah.
Come up a couple times.
I was planning on sharing slides, but I don't think any of us want to stop looking at this comment. So in lieu of sharing slides, I'll just put all the links to what I would have shared in our chat here, and then people can download it and talk about it a little bit. I might minimize my screen just so that I can look at my slides and remember what I wanted to talk about. So as Karen mentioned, the Comet 3i Atlas is the 3rd time we have ever observed an interstellar object passing through our solar system. And the very first one wasn't really that long ago, back in 2017, and that was the object that was named Oumuamua. Oumuamua is a Hawaiian name, and Oumuamua was named through the Ahuehe Inoa object. Ahuehe Inoa means calling forth a name. This is a project that was started with the Imiloa Astronomy Center here in Hilo, and it's a program who's is putting effort towards ensuring that objects that are very, very significant and discovered in Hawaii are given a Hawaiian name. So the name Oumuamua, O with Okina O-U, which means to reach out for. Mua, M-U-A, means like the first, the primary, the principal, and then the repeated mua is an emphasis on that mua. So this is the very, very first time that anything interstellar had been observed passing through the solar system. I've often seen this roughly translated as scout or messenger. It's not an incorrect translation, but it's not like the words don't specifically translate to that, but it's close. And in the chat, I just put in a link to our NORLab website where we have an interactive lesson for classrooms that is based on Oumuamua and looks at some of the research and looks at the data that we were able to get. And one thing that blows me away from just looking at the raw image of 3i Atlas and this is, if you guys get a chance to go through those slides, I have the slides of what Oumuamua looked like in its first observations, and it did not look like that. It looked small, it looked faint, it looks like something that you can hardly see. And so getting into thinking about Oumuamua and thinking about these very, very small objects is that we really only get a little bit of information about these objects. Those of you who have maybe done research on Oumuamua might have seen the picture, the artist rendition of Oumuamua looks like as like this long cigar, but that's not an actual picture. That is an estimation of what we think it looks like based off the data that we got. And the data that we got of Oumuamua was a tiny little dot, and that dot got brighter and dimmer. And so one thing that you can do with data of a dot that's getting brighter and dimmer is to make a light curve in order to analyze how that light is getting brighter and dimmer, and then use that in order to estimate the shape of the object. So in the lessons that I've dropped in, there's a whole interactive lesson that you can do in your classroom, or if you just want to bring it home and play with it a little bit, of how you could be looking at how different types of objects make different light curves and how that translate into what the object looks like. In our conversations with Karen, especially as we've been planning this, we're also thinking about the image versus the spectra, and how the spectra of the image of these objects gives us a lot of insight into what materials are in the object as well. And so I believe some of our observations today are also going to be thinking about spectra.
Yeah, one way to think about the light curve and how you get at the shape, comets are elongated object. This happens to be a remote control, but it is reflected sunlight. Comets are very dark. They only reflect about 4% of the sunlight, so they would look black to the eye. And then as it rotates, you get less sunlight reflected from the smaller axis. And so Oumuamua had a huge brightness variation, which told us it was really elongated.
I was surprised to hear that Oumuamua was still within our solar system. I was in the impression that it was like long gone.
No, our solar system is really big. It'll be thousands of years, but it's long gone from anybody being able to see it. The same with Borisov. Oumuamua is about 48 AU, so Kuiper Belt vicinity. Same with Borisov, it's at about 40 AU. Yeah, they move quickly through the inner solar system, but once they get farther from the sun, it takes a while to get out.
But one thing I was wondering with this as well, just because of my understanding of this object, it does seem like it's bigger. It does seem like it has more of a tail. Is there any expectation that this might be something that could be visible to naked eye observations?
No, it's brightening slowly, which is the characteristic of either carbon monoxide or carbon dioxide. The reason something might brighten quickly right now is if it had a lot of water. But right now it's really warm for CO or CO2. So that means it's kind of in a sort of flat portion of its brightening. So I don't think there's any chance this will be naked eye. Of course, it could break apart. Comets have been known to break apart. They really are like very fragile, dirty snowballs, and often they'll split into a couple of pieces. And when that happens, you tend to expose fresh ice from the inside that's never been warmed up, and then they can brighten quickly. But who knows? There's no expectation that this will break up. I see a question in the chat of didn't it make a convincing case that Oumuamua was actually a pancake? Well, remember, we only got rotation data or brightness data over a period of a week. And in order to really map out the full three-dimensional shape, you have to get this brightness variation multiple times looking from different directions. So effectively, we got it once looking from one direction, and therefore we did not see the third dimension. So it could be a flattened pancake, or it could be more cigar-shaped. We will never know. Unless you send a spacecraft. And in fact, there were papers early on that said you could build and send a spacecraft, and it could get to Oumuamua even now, but you'd have to spend a lot of money and it would take a while to get there.
Speaking of spacecraft, just because it's always brought up when we're talking about these interstellar objects, of the thought of them possibly being alien spacecraft visiting us. What do you think is if that were to be true, what would the observation that we would see to indicate that?
Well, first of all, I do not think this is an alien spacecraft. And I get very frustrated with a certain scientist who keeps claiming that it is without basing it on evidence. You can't just pick and choose from the observations and say, this one fits my idea, the rest doesn't, but I'm just going to throw away the rest. You can't do that. So, admittedly, when Oumuamua was first discovered and we knew it was red, several of us were saying, interesting. And I actually looked up, what does a spectrum of titanium look like? Thinking that might be a good spacecraft metal. And in fact, titanium is red. But just because it's red doesn't make it a specific substance. So I think you would have to have a preponderance of evidence. I mean, certainly if there was a radio signal that had intelligent communication, that would be surefire. If it suddenly changed directions dramatically, that might be an indication. The comets often have a slight acceleration, and that's because the outgassing is not evenly distributed over the nucleus. It can come out in jets, because that may be where there's some buried more volatile ice like CO or CO2 that interacts with the heat very strongly. And sometimes the heat can build up some pressure of the gas under the surface and it bursts out like a rocket thruster. And so you can get slight accelerations on these, which will cause a slight deviation in the orbit. That's typical. But on the other hand, if it made a right angle turn, yeah, we'd have to be thinking outside of the box for that. So there's another question about hypothesis being some sort of hydrogen comet. The reason that people were talking about hydrogen and nitrogen was that you need some sort of gas, which was not observed, to come off of the comet. Well, it turns out that you can't get nitrogen or hydrogen from the ground. So therefore, that's why we didn't see it. But in reality, none of the observations were really sensitive enough for Oumuamua to detect any gas. We only had about a week and it was getting fainter really quickly. And even the Spitzer Space Telescope, which could get it in the infrared and look for carbon monoxide and carbon dioxide, it had to wait until very late before it could even start the observations because Spitzer couldn't point very close to the sun. It had to wait a while. And so those observations were an upper limit. So there was a lot of work on very creative ideas trying to put all the facts together for Oumuamua. I think in total there were a couple hundred research papers written.
So I'm just going to pivot back to 3i now.
Yeah, please.
So we finished the imaging sequence, and Carlene and Pierre right now, they actually took another image. This was an acquisition image. This is to set up for spectroscopy. So we've taken 4-band imaging observations, two images in each band, moving the telescope around a little bit in between each image, again, to remove defects. And on the screen now, you can see 3i right in the center frame there. And you can see it's a little bit off center. And so as soon as that sound happens, Carlene pressed return on our computer. And so there's the direct image. So we want to have the target, in this case, 3i, centered up in the slit. And so that's where the little crosshairs are. And so Carlene's measuring the brightness profile of 3i. That's what you see at the bottom left populated there. That's the azimuthally averaged brightness profile. And then this right here is a slit image. So this is just taking an image through the slit of the sky. So there's not supposed to be anything there. This is just to illuminate the slit so we know where it is. And so there were offsets that were sent to Pierre. So that's actually moving the telescope. And it's really hard to see probably for the text, but this was movements we have our own coordinate system in Gemini called P and Q. So this is perpendicular to the slit is P, and Q is parallel to the major axis of the slit. So in this case, the vertical direction. And so the movement was about 1 to 2 arc seconds in each dimension. And so this thing is moving fast. It's tough to catch. And so even with a really accurate pointing model, we're off by about an arcsecond. But as soon as this next image comes through, we'll see if they were successful in centering the slit. Right on cue. And there it is. Nice shooting. So they're going to measure again. This is now through the slit. This is an undispersed image, so this is collecting all the light. And our software has suggested that we don't actually send any offsets. So we are going to be moving on to getting a spectrum here.
Nice.
And so again, we're breaking up the light into its constituents. Awesome. Breaking up the light into its constituent parts to get a rainbow. And so this observation is going to be quite a bit longer than the imaging observation. So somebody asked about how long the imaging observations were, and I saw that was answered. So those are 30 seconds to 2 minutes or so. And these observations here are going to be about 8 minutes apiece. So we're going to take looks like 4 spectra along with some calibration data. So we're just setting up now. I can actually let me go to the screen. Yeah. Okay. So, oh, maybe it's not active. So this is the instrument status display of GMOS. And let's see here. Maybe this is an old one. Are you configuring right now, Carly? So normally when we move from a imaging observation to a spectral observation, so this is another schematic that we have. So now, so going back to this telescope status display, so we're just looking at this part of the light, so just where the instrument is. So this new schematic here is just showing once the light is entered into GMOS, what's happening to that light. And so the light comes in up here. It hits our on-instrument wavefront sensor at a particular location where our guide star will be, so we can track the telescope, track the target more precisely. And then if this were updated, this is our mask. So the MOS portion of GMOS has, we can take multiple spectra at once. In this case, the mask is just a 1 arcsecond long slit. So we're masking out all of the light except for what's in this 1 arcsecond wide slit. And then we have filters, which allow us to tune which wavelengths we want to look at. Then a grading, this is the dispersive element in GMOS. And so right now it reads mirror. But if it were updated, it would read a particular name for a grading, because we have a lot of different gradings at any given time. We have 3 in our instrument, but we swapped them out many days. And then so that disperses out the light, makes the rainbow, and you can disperse it out so it covers all the way from bluer than what humans can see to redder than what humans can see. And so you have to make a kind of choice. In this particular observation, we're going very blue. So we're basically going as blue as GMOS can go, almost to the atmospheric cutoff. So I think our bluest wavelengths that we'll observe are somewhere around 360 nanometers. So yeah, much bluer than humans can see. And then we're going to go as red as about 800 nanometers. So just about the range of human seeing on the red side. And then we have a shutter and then the detector there. And so I'm not sure, Carlene, are you actually taking the spectral observations right now?
Yes, select the program. It is I see you have the SecExec open, but it is in the calibrations. Yeah, select the program there.
So I'm in non-interactive mode, so I don't want to mess with your stuff.
Okay, so go I will put the SecExec there.
Okay, sounds good.
Yeah. Can you see?
Yep. Okay. And is your ISD not updating? Because I see the GMOS ISD, it still reads like mirror and shutter closed.
Yeah, everything's fine. Timos. We are halfway the first spectrum.
And no, the bottom right, the ISD.
No, that's not my.
That's not yours?
That's not my. No.
Ah, okay. Okay, maybe it's a stale screen then.
Yeah.
But yeah, so we're about halfway through the first spectral observation. So as soon as that comes out, then we'll take a look at that. Since we're getting kind of close to the end of the session, I wanted to pass to Manuel if you wanted to talk a bit about the connection of 3i to Chile and Chilean astronomy. Carlene, I see that you're looking at so we've got our first spectrum. It's hard for me not to get like super excited, but I got super excited about well, one has to be tempered here. So looking at raw images is not the best for science. But I thought I saw some emission in the blue side. So blue is actually to the right here and red is to the left. But we have skylines. These are the vertical lines here. So this is emission from various species in the atmosphere. We have all these little white streaks that are all over the detector. These are mostly cosmic rays that are coming in from highly energetic sources. Our detectors are very sensitive to photons, all the way from blue to red. But that also means they're sensitive to cosmic rays. And so I thought I saw an emission in the bluer side of the right detector. Turns out it probably is just a patch of cosmic rays. It even looked off-centered from the trace. So yeah, this is one has to be cautious, and so the data will be processed, and we will take this sober approach of removing all the defects. But yeah, this is the first spectrum of the source for tonight, and it looks like we're getting tons of signal here. So that's wonderful. So we can't exactly point out any emission features besides the skylines. But given how bright the continuum is, so this horizontal trace here, given how bright that is, this will allow Karen and her team to put very stringent limits on any emission that's coming off from any species on 3i. So I think there'll be one more. Let's see. So we're still taking observations, of course. So I think the next spectrum will come in shortly. I actually, Carlene, are you guys running the spectral, like the Dragon spectral reduction, real-time spectral reduction there?
Spectral reduction? No.
So we at the north, I don't know if you guys do the same thing in the south, but we run like the reduction in real time, and then there's a spectral viewer that allows us to see like a kind of pseudo reduced spectrum. Yeah, exactly, yeah. Yeah, and I guess since there's no arcs and flats.
This one is pre-processed, so it has some of the things removed. Although you can see a lot of cosmic rays.
Yeah. So as this builds up over, so we have a data reduction package called Dragons, and this is being run as the observations are being taken, and so it's doing all of this processing of understanding which wavelengths correspond to which locations, trying to remove the skylines, these vertical lines, trying to understand where the source is. You can actually see a secondary source just up of a really bright source. There's another horizontal trace there, so it'll detect that. In this case, it didn't, but as it builds up more and more observations, it will. And it will flat field the data and do other calibrations. And so as the observations come in, we'll be able to see actually these chip gaps disappear and all the other things that would be done normally under scientific calibration. So are you guys, you're almost done with the second spectrum now?
So Brian or someone, I see that Ben Yang is in the chat. She thinks she sees the CN emission in the rod spectrum, and
Okay.
she's
Yeah.
our resident spectroscopist for comets. So if she can
Oh,
be
wow.
elevated to
Awesome.
speak,
Awesome.
that would be good. If you could elevate her, Bin Yang.
Yeah. Jamika, do you mind doing that?
Yes, so make Bing Yang co-host so they can chat with us.
Yeah.
Yes.
Gotcha. One moment.
Yeah, I don't remember
Actually,
if she's in France right now or back in Chile at this point.
Carlene, there's also a way to show the 1D spectra. It's usually with the if you go to it's a web interface, and it's like a 1D spectral viewer.
Yes, from this one, or when I open the Auto Redux, I just have this thing.
Okay.
I'm not actually using Dragons, I'm just using the quick look. We have a thing to just to check the scene if everything is fine from that, but not. Cannot
The 1D
interact
spectra.
with this.
Okay. Okay. So the when I say one-dimensional spectrum, I mean it's actually still two dimensions, kind of. But so this is showing spatial up and down, and dispersion or wavelength left and right. Blue is on the left here, and red is on the right. And what we do to create what's called a 1D spectrum is we make an extraction. So we basically sum up all the light within a certain spatial region, and then just plot brightness or flux density versus wavelength. And I don't have a good enough eye to be able to see emission here. I'm used to it for galaxies, not for comets. But Ben, if you're able to unmute,
Yep.
Very happy for you to tell us where you see it.
Right. So basically, to the left, you see there's two dips. Very end, that's the H and K absorption line from the sun. So at the very edge, that's usually around 400 nanometer. And then to the left of it, there's a emission feature. That is where the CN band should be.
Oh, yeah. Let's
So
see
this
it.
is a spatially extended feature there.
Yeah, so that's like usually when
Oh,
you see
awesome.
these two little dips, that's the H and K line as a reference. And then to the left, that's the blue end of the
That's a
spectrum.
perfect match,
And
Carlene.
then you
that
can see
red
that
line.
emission feature. That's the CN for sure.
Oh gosh. Okay, that is amazing. Yeah. So this is calcium H and K. Yeah, at 38 something, 3900.
Yep.
Woo, neat, super neat, and it's extended spatially. So that's
Yeah, so the
also
clearly is
really
coming
awesome.
from the comet.
Okay, well that's wonderful. I'm super happy to see that. Okay, we're getting close to, we're actually past time. So I think that's a great place to end it for these observations. We're going to continue to take observations. There's going to be more calibrations, but we're going to end the session for now. But I wanted to pass to Bryce because we'll have more observations both from the north and from the south. So more from the south pre-perihelion. So Bryce has an imaging campaign coming up all the way until we can't see it anymore. And then when it reemerges from the sun, Bryce has a spectral campaign and imaging campaign up here. And then we're planning on hosting another Shadow the Scientist session when it comes out from behind the sun here in the north. So that'll be awesome. So Bryce, might you talk just a bit about your upcoming or your current programs and your upcoming plans?
Yeah, sure. So we are planning on imaging the comet in U, G, R, and I bands at Gemini South. I'm probably going to offset it from tonight since we got some data in U, G, R, and I tonight. And then we will be observing the comet every 5 days or so until the comet is no longer observable at Gemini South. As you could see there, the images were looking quite good. You could see an anti-solar tail. You could see the comet in all 4 different filters. So it's valuable information because we did not see a anti-solar tail before with the comet. Before we were seeing different morphology. We're actually seeing a tail going in the direction of the sun. So now we're starting to see it appear in the anti-solar direction, which is quite interesting. So we're also going to be taking near-infrared spectroscopy, flamingos to try and detect any presence of water ice grains in the coma. So it's something that we're been monitoring with near-infrared spectrographs at a variety of different telescopes, including VLT, as this was mentioned before, and Keck before that. And when the comet goes into solar conjunction, and in a few weeks, we'll have to wait a couple of months for us to observe the comet again. And starting in late November, we will observe the comet again, but from Gemini North, because the comet will be at a positive declination. And right now, the comet is about minus 15 degrees declination. And when it emerges from solar conjunction in late November, it will be, I believe, around 5 degrees declination, positive 5 degrees declination. And so we will switch from Gemini South to Gemini North, and we will take multiple spectra of the comet as it emerges from perihelion. When it emerges from perihelion, it'll be even closer to the sun. Right now, the comet's about 2.7 astronomical units from the sun. When it emerges from perihelion, leaving solar conjunction, the comet will be about 2 astronomical units from the sun. So it'll be even closer to the sun. And there can be this delayed kind of reaction where the activity of the comet can increase some period of time after it passes from perihelion. The perihelion passage is in late October. So in late November, we could see the comet approaching its peak activity, as it's the delayed onset of increased activity due to the penetration of heat through the comet mantle. So I think we're going to be getting some amazing data. As you saw, the data are looking great from tonight, and there'll be more of it to come.
Yeah, so I'm showing the orbit viewer from JPL Horizons here. And this is, you can actually, public URL, you can just, all you have to do is type in at the top, you do add remove object, and then you just type in 3i. And it'll show you the orbit, or the projected orbit. And so this you can set to any date. So right now we're at August 27th.
Yeah, I was going to say what we saw with the second interstellar object, 2I Borisov, we saw a outburst occur in the comet after it left perihelion. So no promises for this object, but comets can undergo various structural changes, thermal changes due to the heating from the sun. And in the case of 2I Borisov, it outburst and fragmented. It didn't completely disintegrate, but pieces of it, boulder-sized pieces of it, were ejected from its surface. So getting regular monitoring of this comet is valuable in that case, because we can. The comet is not a static thing; it's constantly evolving, and keeping eyes on it as it is entering and leaving the solar system will give us a more complete picture of how it evolved.
Wonderful. That's a wonderful place to leave it. And yeah, who knows what's going to happen when it reemerges from the sun. So for everybody interested in that, I mean, how could you not be interested in that? But everybody who's interested in that, we will post at some point another session for Shadow the Scientist post-perihelion with Bryce and his team. I want to thank everybody for joining us from all over the world. I want to especially thank Carlene and Piera for allowing us to shadow them at Gemini South. Karen and Bryce for joining us and explaining all the science behind things. Elena and CE, I guess CE just took off. There she is. Okay. Elena and CE from joining for Tucson. Jamaica from joining, and everybody up at the Viz from joining from the Viz. Emily for joining here in Hilo. This has been a really wonderful experience. It was a lot to pull together, but it was really awesome. It's super cool. Those are the moments inside. I mean, observing, there's a lot of downtime and we got to take this calibration, and then all of a sudden you see that signal pop out, and it's really wonderful. And Ben for spotting it and for pointing it out. So.
Yeah. And while we're not going to have another Shadow the Scientist session for the Comet until probably after perihelion, there is another Shadow the Scientist for Gemini North on Sunday of this week, after our Tanabata block party here in Hilo. It is Sunday. Please sign up for those sessions as well.
Yeah, and Jamika will also be at the biz for that, and actually our head of engineering and instrumentation, who is retiring on Friday here at Gemini North. Beware, Gemini North PIs. He will be joining us for that session.
Oh, that's a special.
So he'll be able to like answer all the questions, and he's just an amazing person and amazing engineer. Single-handedly kept telescope running many times. So it'll be a pleasure to be able to.
After he retires.
Yeah. Even willing to come back 2 days after he retires to talk about Gemini. So super excited for that. And for everybody who joined us today, we will gather all the materials that we had, Lena's presentation, Emily's presentation, Mama's presentation. We will put those, we'll email those out to you all. We'll also likely be putting together a color image. So Jen Miller here, along with the imaging team, they're going to take the observations that were taken tonight and make a nice color composite image. So if we're able to do that in a reasonable time, we will also email that out to everybody, and feel free to use it or put it in your classrooms, or I don't know, carry it around with you, show it off to people that you saw these observations. Any parting words from anybody else?
If not,
in English and Finnish.
If there are no other words from anyone else, I would just like to again reiterate what Brian said. I'm so grateful for everyone who joined us today, all of our experts here, and all of you who joined us virtually and here in person at the Mauna Kea Visitor Information Station. This has been a thrilling and exciting session, and made extra special because this is something that is so rare and unique for us to be able to observe. Thank you to everyone for bringing us together and making this possible. We'll see you in a future Shadow the Scientist session, maybe on Sunday with Gemini North.
Yeah, I just, real quick, I just want to say thank you to Elena for letting us have some time to observe the comet, and it provides a fantastic scientific opportunity for us.
Thank you. I'm very excited that how it came out. So thank you both for your guidance in organizing this.
You're welcome.
Okay. Thank you, everybody.
Thanks.
And we'll see you again.
Thank you, Jamika.
Before you know it.
Bye-bye.
Bye.
Aloha.
Aloha.
E aí, falar pra vocês, eu assisti isso 3 vezes, tá? Assisti ele a primeira vez, depois assisti ele quando estava editando, depois dele pronto assisti ele de novo. E acho que eu vou assistir mais umas 2, que é muito bacana, né? O que vocês acharam? Comenta aí, né? Gostou? É lógico que você não vai ter em casa um telescópio do porte do Gemini, né? Com um telescópio de 8,1 metros aí é muito, né? Mas dá pra você ter um telescópio pequeno, observar. Nós temos um cometa novo aí, gente, tá ligado? É o cometa Shivan 25, descoberto hoje pela sonda SOHI, que já estava saindo do periélio. Está extremamente brilhante, dá para ver. Magnitude 7,5. Então, já corre lá no nosso parceiro, na Foto Astro, e vai buscar o seu telescópio, tá? Na descrição desse vídeo eu já deixei para vocês aí o link da Foto Astro, e também deixei a opção de 3 equipamentos que eu escolhi a dedo para você iniciar. Então, com menos de R$1.000, você compra o primeiro dos equipamentos que eu deixei. E não é equipamento ruim, não é meia boca, não. É coisa boa. É Skywatcher de alta qualidade. Tá certo? Então, corre lá e dá uma olhada. Comprando através dos links aqui, você já está comprando com desconto. Se não, só usar o nosso cupom NERD50, tudo junto. Beleza? Outra coisa, gente. Onde? Acha aí. Sem ser o canal do Gemini, onde que vocês vão ver um trabalho desse jeito aqui? Não vai ver, não tem. Né? Não tem lugar nenhum, ninguém se preocupa com isso, de trazer informação de verdade, da fonte, o mais limpinho, né? Pra vocês beber aí e poder usar, né? Ninguém preocupa com, ninguém tá nem aí, não, isso quer só ganhar dinheiro mesmo, a grande maioria, tem gente que não, mas a grande maioria tá só nessa onda aí pra ver o que dá dá view, que dá muita visualização e tal, é isso que eles querem. Tá certo? Então, gente, o nosso trabalho ele é árduo. A gente, inclusive, mantém um canal aqui. Eu completo todas as despesas ou pago todas as despesas do meu bolso. Tá? A gente tem o editor aqui, Nerd aos 18. Vocês acham que Nerd aos 18 recebe do YouTube? Que o que o canal do YouTube aqui rende paga Nerd aos 18? De jeito nenhum. Tá? Primeiro que assim, a gente não recebe todo mês. Costuma, às vezes, a gente esperar até 3 meses para receber, para atingir as métricas do YouTube. Por isso que a gente precisa fazer esse canal crescer. Né? E aí, como é que o Nerd aos 18 fica? Né? Vocês viram que o meu relógio que ficava aqui, agora não está nem aparecendo, não. Mas ele parou de trabalhar porque não tem pilha. Então, nem relógio trabalha de graça, quanto mais Nerd aos 18. Né? Então, assim, quando o YouTube não está pagando, eu pago o Nerd aos 18 do meu bolso. No mês que o YouTube paga, né? Aí eu completo só. Né? Outra coisa, microfone aqui bacana, camerinha legal, cenário, tudo sai do meu bolso, gente. Não tem jeito. O que o YouTube rende, na verdade, ele dá uma compensação que é muito pequena para o trabalho. Então, por isso que está aí o Pix do canal para vocês. Quem puder nos ajudar a manter esse trabalho aqui, dar essa força aí. Pode ser qualquer quantia, tá, gente? Eu não estou pedindo que você faça um Pix aqui de R$1.000 para a gente, não. É qualquer quantia. 50 centavos, R$1, R$2, R$5, R$10, o que você conseguir dar. Tá? Ah, né? Mas 50 centavos é muito pouco. É pouco, mas se você der 50 centavos, eu não vou tirar 50 centavos do meu bolso. Então, qualquer quantia que entrar aqui é uma quantia a menos que eu vou custear. Tá certo? Então, conta aí com a ajuda de quem puder nos ajudar. Outra coisa, vamos fazer esse vídeo agora atingir o YouTube inteiro? Chegar informação de qualidade bacana para as pessoas? Uai, Nerd, como é que eu vou fazer isso? É só usar o sacolão youtubístico, galera. Qual que é o sacolão youtubístico? São todas as ações que vocês podem fazer e devem fazer para ajudar o canal. Senta o dedão no like, senta o dedão no botão hypar quando ele aparecer, comenta aqui, né? Fala o que você está achando, o que você acha do canal, bota suas dúvidas, o que você quiser, né? Inscrevam-se no canal, compartilha ele para os seus amigos, não é? Isso tudo aí vai fazer com que o YouTube entenda que o nosso canal é de relevância, que vocês interagem com o canal, com o conteúdo, e e com isso o YouTube entrega ele a cada vez mais pessoas. A gente precisa dessa força aí, tá certo? Outra coisa, você já deixou aquele salve pro Alfredo? Se não deixou, a hora é agora. Já vai aí nos comentários, já manda lá um grande salve pro Alfredo, agradece o Alfredo aí, porque... inclusive te agradecer mais uma vez, né, Alfredo, por mais um conteúdo incrível que você está mandando para a gente aqui, tá? Lembrando para vocês também que na descrição desse vídeo tem o portfólio do Alfredo, né? Então já vai lá na descrição, visita o portfólio do Alfredo, que é, além de outras coisas, uma pessoa muito culta, é artista plástico em Portugal. Então já visita o portfólio, conhece o trabalho do Alfredo aí para vocês verem que o cara é feríssimo mesmo, tá certo? Então é isso aí, galera. Grande abraço e até o nosso próximo vídeo.